All right, we're going to look at graphs of polynomial functions and what you can determine about them just from their equation. More specifically, we're going to look at from that leading coefficient, what does that tell you? That constant term on the end, what does that tell you? And then the degree of the function. First of all, what the value of the degree is. And second of all, whether it's odd or even in general, what can that tell you? All right. First thing we're going to focus on is the degree, right? The value and whether it's odd or even. And we're just going to look at the base functions, right? X squared, x cubed, before we start involving all these different terms here. So I have a graph here set up already with all the base functions. Y equals x, or x to the 1. Y equals x squared. Y equals x cubed, x to the 4th, x to the 5th, x to the 6th, and we'll look for some patterns here and see what we can see. Y equals x starts low, ends high. Right? That's just because the y value is equal to the x value. When the x value is positive, y value is positive. X value is negative, y value is negative. Now compare that to x squared. X squared, as you go to the right, the y value is positive, because when you square a positive number, you get a positive. But it's also positive on the left, because when you square a negative number, you get a positive value. So x squared goes up in both directions, which you get that parabolic shape where both ends go up. It starts high and ends high. Now, when we start to look at x cubed is going to do something different again. Although it's not so different than one of these two. Right? It has some similarities with this, even though they look quite different. It starts low and ends high. And the reason is for this is when you think about the operation involved. When you have a positive number and you cube it, you raise it to the 3rd power, right? Like 1 cubed is 1. Those graphs actually pass through the same point there. Right? 1 cubed is 1, that point. Or if you extend this, if you look up a bit higher here, 2 cubed is 8, that point there. Right? As you go to the right, you cube a positive number, you get a positive number. But when you go to the left, when you cube a negative number, negative times a negative times a negative, it gives you a negative number. Right? So negative 1 cubed is negative 1. And negative 2 cubed is negative 8. So it's going to go down to the left and up to the right. It's similar to a line in that way. And it's different than x squared, right? Now, let's look at the next one. X to the 4th. X to the 4th is that green one. And the one that it's similar to is x squared. All right, we'll take those other two away. Now, the shape is different. It's flatter on the bottom. It takes kind of longer to start curving up, but then it's quite a bit steeper, right? Before you get to 1, it's below this parabola. After you get to 1, it's a lot higher, because when you raise a number to the 4th power, if it's bigger than 1, it's going to be a big number here. So while you have 2 squared is 4, 2 to the 4th power, we got to look at 16 here, that value right there. 2 to the 4th is 16. When you raise a negative number to the 4th power, since it's an even power, negative 2 times negative 2 times negative 2 times negative 2, you get a positive number. So x to the 4th is going to be both directions. It's going to go up. All right? It's going to go in the same direction. It's going to behave the same way as x squared does, and different than these, right? It has to do with raising a negative number to that power. Let's look at the last one here, which is, let's get all of them away, and then we'll look at x to the 5th. X to the 5th is going to behave like x to the 3rd, only it's going to be steeper, and that's the same as x to the 1st here, right? So let's go back to, say, there, so we can see it a little better. Again, it's even lower than x cubed. They all pass through this 1, 1 here, right? Because raising 1 to any power is always 1, and negative 1 to any odd power is always negative 1. But it's going to behave like those just because of the same way of the nature of raising negative numbers to powers. If you raise a negative number to an odd power, it's negative. Raise a negative number to raise a positive number to an odd power, it's positive. So you might predict then that x to the 6th is going to look like the other two even degree functions here, x squared and x to the 4th. All right, and it's different than these two odd ones. All right, so those three odd ones, odd degree functions, or sorry, those three even ones, even degree functions, all have the ends going in the same direction. Their end behavior is what you talk about their end behavior. What happens to the ends as you go out towards negative infinity and positive infinity? They go in the same direction. When it's just x squared, x to the fourth, x to the sixth, they head for positive infinity, positive infinity. Whereas if you have the odd degree ones, as you go infinitely to the left, they go infinitely down. As you go infinitely to the right, they go infinitely up. Now we're going to look at one more thing here before we leave these basic graphs. What happens when you put a leading coefficient in front, whether it's negative or some other value. And we'll start with our linear function. Now you, I'm sure, know that if you put a negative number in front of this x term, right? Right now this is like 1x. If I make it negative 1x, it's going to go down instead of up. You change the end behavior. Now it starts high and ends low because of that negative number in front of x. If we do the same thing with a parabola, with x squared, you know that instead of both ends pointing up, starting high and ending high, both of them are going to be down. It's going to open downwards instead of upwards, right? The even ones open up, or they open down. If you put a negative, it's been vertically reflected across that x-axis. Same is going to carry through with these other ones. With if we look at x cubed, if we put a negative in front of that, you're going to have that, negative x cubed. Negative x cubed starts high and ends low. It does exactly what the same thing as negative x does, right? Negative x goes down instead of up. And then when you keep moving on with the pattern here, if we put this on parabola back on here, and I'll put my negative back there that I had, this x to the fourth is going to behave the same way. It's going to open down if you have that negative in front. That coefficient in front of that term affects which direction it opens if it's even. Same thing's going to happen with this. Opens up. Unless you have a negative in front of that, it opens down. And then the odd ones, they don't open a certain direction. They behave like lines. The odd ones behave like lines. So if you have a negative in front there, turn off all the even ones. Turn on the odd ones. And if I put a negative in front of that x to the fifth, then it slopes down like the line. All right, so that's the importance of that leading coefficient being positive or negative. We're going to look now at functions that have a lot more terms in them. And to do that, we're going to look at a different graph here that has already some polynomials with lots of different terms in them. Each of these, this is a linear function, degree 1, quadratic, degree 2, cubic, 3, quartic, 4, quintic, 5. Each of them has as many terms as it can have, all the other lower power terms as well. The one that's showing there is obviously a linear function, 0.5x minus 1. Now you already know that both of those terms, you can tell something about the graph from them, the second one being the y-intercept. The first one, that leading term, having its coefficient being the slope of the graph. Now the fact that it's positive here means that thing is sloping up to the right. If that were a negative, of course, it'd be sloping down to the right. We could talk about a term called its end behavior, the end behavior of a function. The end behavior is talking about what happens at the ends of the graph. Now, of course, it doesn't end. It extends infinitely either direction. But what's happening with this is it's extending down. It starts low down on the left and ends up on the right. Starts down, ends up. If you want to use the numbers of the quadrants, the numbers, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. This one starts down in quadrant 3 and ends up in quadrant 1. Whereas if you put that negative back in there, it's going to start... Let's change the window a little bit. It's going to start up in quadrant 2 and end down in quadrant 4. If we look now at the quadratic, the quadratic, the fact that it has that leading coefficient not even written there. It's a 1. It's positive. The fact that it's positive, you already know that that thing opens up. If we talk about it in terms of end behavior, the end behavior of this thing is that it starts up in quadrant 2 and ends up in quadrant 1. Right? Both ends are up in this case. If we were to put a negative in front there, right, we would change the function, obviously. It's a different function now. But now its end behavior is it starts down in quadrant 3 and ends down in quadrant 4. All right? So you can tell from that leading coefficient something about what you call the end behavior. And that is going to follow just the same as we had when we had the base functions before, right? The base function, base quadratics, like that. Starts up, ends up. It's going to follow the same way for these cubic functions and higher degree functions. If we look at this cubic here, you have that. There's your cubic. Now it looks quite different than just the basic x cubed graph that we looked at when there's all those other terms, but there are some similarities. If you look at the end behavior of this thing, you see that it starts low in quadrant 3 and ends high in quadrant 1. Alright, that's the way, even though it turns around a couple times here, it behaves the same way. Now, I'm going to compress it down here a little bit, the scale. I'm not changing the graph, I'm just changing the scale. Now, it's hard to see that grid's all compressed, but it's starting low, it has a couple turns and ends high. The basic cubic, right, if I take away all these other terms here, looks kind of the same, even though it doesn't actually turn all the way around, but it has those similarities, starts low, ends high. If we look at the fourth degree function there, that's what a fourth degree function can look like, with a bunch of other terms involved there. It obviously looks quite a bit different than that basic fourth degree function that we looked at, but again, there's similarities in the end behavior. If I compress that one down, right, it starts to look more like that basic graph. All right, it looks quite a bit different when I have this like this. If we get rid of all these other terms temporarily here for a second, looks like that, right? Now, even though close up that looks quite a bit different, again, if I compress that down, looks starting to look quite a bit the same there, right? It's hard to tell, but and that fifth degree function there, that looks quite a bit different than the fifth degree function we have, again, because of all these turns. We're going to talk about that in a second. But it does have the same behavior, that it starts low and ends high, just like this, which we'll look at real quick here. Like that, right? Starts low, ends high. It's just that it does a few twists and turns in between. Now, speaking of the twists and turns, we're going to try and make some connections here between that and how this is affected here. Now, these are just some examples of these things. But let's start back at the beginning here with our linear function. Straight line function, this is degree 1, x to the 1, right, that one. It starts low, ends high. There's no turns at all. 0 turns involved there. It just goes straight up like that. When we had our quadratic degree 2, we had 1 turnaround in the graph. Right? We had 1 turnaround in the graph. Or we had 2 different kind of sections. We had the part going downhill here, and then we had the part going uphill. You could split it into 2 parts. When we have our cubic here, this is again just an example, but it has this part that is going up, then it turns around, has this part going down, turns around, has another part going up. It's degree 3, and it has 3 distinct sections here. Or you could look at it as it has 2 turns here. Degree 4 here, when you have our fourth degree function, now this one has 3 turns in it, 3 turnarounds. Or again, you could look at it as a downhill, or a part going down, part going up, another part going down, part going up. You could split it into 4 different sections. Degree 4, it can have 4 different sections to it, or it can have, or you could look at it as the number of turns. The number of turns it can have at most is 3. It might not have 3 turns. It might only have 1 turn, right? Because we've seen that when we just had our basic x to the 4th graph. That only has 1 turn. Just because it's x to the 4th doesn't mean it's going to have 3 turns in it, but it could have that. It can't have any more than that. Just like a parabola couldn't have more than that 1 vertex, that 1 turnaround. And then just to complete things here, let's look at our 5th degree function. It's got 5 pieces to it. Up, down, back up again. Or you could look at it as a number of turns, right? 1 turn, 2 turns, 3 turns, 4 turns. It doesn't have to have that many, right? Because, again, we could do this. That's only got 2 turns to it, right? 1 turn, 2 turns there. And it doesn't even start going back down again. It has this uphill piece. And even though it kind of looks like it levels out there and it keeps going, it actually, if we extend this, hard to see, but it's actually only 1 point in there where it's gradually getting there. But there's only 2 turns in it there. Just because it is degree 5 doesn't mean it's always going to have that many turns, but that's the most it can have. It can't have more than that. All right, so number of turns or number of sections of the graph related to that degree. And then the last thing is, if we go back to our linear function here, as we said earlier, that term being the y-intercept, and the same goes for this, for the quadratic. That constant term in the end is that y-intercept. Now the reason that is because if you substitute in 0 here into this function, right, because that's where the y-intercept is. The y-intercept is where x is 0. If you sub in x is 0 into this, you get 0 squared minus 2 times 0. All you're left with is this minus 3. All the other terms are 0. That's why it was for the linear function, right? This term becomes 0. That's why it is for the quadratic, right? This term becomes 0, this term becomes 0. You're left with negative 3. That's going to be true of all these other ones here, right? This one has a y-intercept of negative 6. Look at that. That's its constant term. If you substitute x equals 0 in there, 0, 0, 0, all the other terms are going to become 0, and you're left with just negative 6 on the end here. Just make that connection with the other ones here. When you have this 4th degree function, the constant term's negative 4, its y-intercept is negative 4. Again, if I change this, if I make this something else here, if I make this negative 7, it's going to be down there. Actually, when you change the constant term of a polynomial like that, you're just shifting it up and down. You're doing a vertical translation. So whatever that constant term is, that's its y-intercept. That's an important thing to know as well, right? Negative 3, negative 3. Even if you change all the other stuff, if I start changing some of these other terms in here for this, say this 5th degree function, if I make this, even if I do a slight little change, it can do a lot of different things here. Now that's looking a lot different, right? We have to change the scale here to see what's happening. Right? That's still a 5th degree function. It's hard to see all those twists and turns, but that y-intercept is still negative 3, even though it looks like the 4 is beside it. It's 1, 2, 3, negative 3. It's got 1, 2, it's hard to tell. It might even be 3, 4 turns there, but it's really hard to see those two. But you know for sure end behavior, you know for sure y-intercept, and possibly number of turns. Right? If you change other things, you might have other changes here. If you make this negative 8, okay, you start to affect the shape of the graph, but some of those other things don't change. All right, we do this. Now we've made it a bit different here, but it still has that same end behavior. If I wanted to change the end behavior from low to high, what would I have to change in here? I'd have to change that first term. Right? If I make this first term a negative now, that's what's really drastically going to change it. All right, now it seems like that's a pretty simple graph for all those terms, but that's what happens sometimes, right? But the thing you know here, the negative leading coefficient starts high and ends low. Now I should look around here a little bit because it may be that it does one more up and down off of what I can see outside of the graph. But it looks like I'm okay. Now I can also maybe just start making some other changes to a plus here. Now if we start changing some of these other terms, maybe we'll get it to look a little different here. But we don't want to play around with this too much here. See, so that one, now again, this only looks like it has a couple turns in it, but it has this wider one here. Still that's the most it could have is 4 turns, even though it's only got 2. Okay, so that's a basic introduction to the graphs of polynomial functions. Now there's going to be a lot more stuff that we're going to look at, but for now we've just looked at those three different aspects of the graph. We've looked at leading coefficient and what that tells you, whether it's positive or negative, tells you the end behavior. We've looked at the degree and whether it's odd or even and kind of the general nature of the graph. And then the value in terms of how many turns the graph can have or how many individual sections the graph can have, the ups and downs. And then we looked at the constant term and how that tells you the y-intercept, just like any other kind of function that you know, if it's in that form. All right? That is it. Introduction, part 1 of graphs of polynomial functions. Later on, we're going to look at when we can do some algebra with this and determine some other things.